In this video, we're going to cover our integral review chart. We're going to have integrals here in the middle. We're just going to go through all the different things we've learned about integrals, and a few things we haven't learned yet we'll list off. We're going to start off with area under the curve. I'm going to use one color. Here, this is kind of the definition. And this is how we began looking at integrals, was the area under the curve. And we started by estimating using rectangles, and I'm going to say estimate by using Riemann sums. In particular, we had left, right, center, as well as trapezoidal. Now, from these sums, we can, or we did, use the limit of infinite rectangles. So that's the limit as n approaches infinity of the sum of k equals 1 to infinity of whatever our thing is. Remember, this was how we got from the rectangles these sums to the actual integral. So this area under the curve is kind of what defines it and what allowed us to do that, to do the calculus, the integral calculus that we did. Now, a couple other things about area under the curve is we can use area to find the integral, or we can use integral to find the area. It works both ways. So sometimes you'll be given a graph like a semicircle, and you have to find that area to calculate the integral, and other times you'll be using the integral to calculate the area. That's kind of where it came from. I'm going to stay in red to talk about the calculations. We talked about indefinite integrals. And remember, this is just finding the antiderivative, so taking the derivative and going backwards. And the other thing to note about this is when we use the plus c. Okay. Now, let's talk about a couple strategies. So we're going to keep this in the red. Strategies or rules to calculate. One of the big ones is use substitution. That allows us to do complicated integrals. Also, we need to remember that integral of 1 over x dx equals the natural log of x plus c. And we had some trig rules. We know that rewriting helps. Another very important one is the general power rule. And I'm going to list that one out. So the integral of x to the n dx equals x to the n plus 1 over n plus 1 plus c. So those are some of the basic strategies and rules to calculate, other than just remembering that we use the opposite of derivative. We go backwards. Now the next thing I'd like to talk about is the first fundamental theorem of calculus. And this is what we call the definite integral or definite integration. That's when you take the integral from a to b of some function of x dx. That equals the antiderivative evaluated at b minus the antiderivative evaluated at a. Okay, and remember this is Math 9 on the calculator. We can do that. This results in a number answer, not results in a number, not an expression or an equation. This just gives us a number. Okay. Now, the second fundamental theorem of calculus, we'll abbreviate that. That is when we take the derivative of an integral of f of t dt, this is going to equal f of x. So the derivative of the integral cancels out, and I'm going to write a as g of x. If we have something up there that's a function of x and not just x, then you put the function in and you multiply it by the derivative. So that's the second fundamental theorem of calculus. So we talked about the area and how we found that to use, we use that to find the actual integral. Talked about indefinite integrals and rules, strategies to calculate that if we're doing that by hand to get the antiderivative. And then the first and second fundamental theorems of calculus. And so now largely what we need to talk about are different applications. Let's see, there's one more I'm going to add here in blue. And this is the average value of a function. So to find the average value of a function, f of x, let me write that here just so we know. So to find the average value of a function, you go 1 over b minus a times the integral from a to b of f of x dx. That will give you the average value. So that's just a piece of information about this function. And now what we're going to look at are a couple different applications. And a couple of these we haven't talked about yet. And so we'll list those knowing that we'll talk about it later. Before we go on to applications, I would like to talk about one that I missed here, properties of integrals. A lot of these properties make sense if we have the integral of, I'm just going to abbreviate, f plus g of dx. We can split that to be the integral of f dx plus the integral of g dx. Another one is if you have a multiplying constant multiplier, you can pull that out. And I think we've used these enough that we're fairly comfortable with that. One that I want to list is if you have the integral from a to b of f of x dx and you switch it from b to a of f of x dx, then it gets a negative. Which makes me remember here, area under the curve. Let's add one more piece here that says area below x-axis is negative, and area above is positive. So now let's go to different applications. There's a lot of different ways we can use this, but we're going to generalize it here to an accumulator function. This is where we are just going to be adding up little bits of something over time. So add a bunch of whatever the equation is about over time. Okay, and over time is your t or sometimes your x. An example of that is if you had an equation that measured or showed the rate at which water is entering into a trough, then if you take the integral of that, that's going to give you the amount of water put in over time. So you're accumulating all of that water into that trough. As you do the accumulator function, if you have an initial value, so let's say on that water trough we had water already in it, then you would put how much water was in it plus how much was entering in from A to B of f of x dx. A specific one that I'd like to talk about is position, velocity, and acceleration. So if we do the derivative of position is velocity, derivative of velocity is acceleration. But if we take the integral of acceleration is velocity, and the integral of velocity is position. So that allows us to, again, accumulate a bunch of velocity to determine a position over time. And that's one specific application we've done some problems and we'll continue to do some problems on. Two more that we're going to add at this point in time are ones we haven't talked about. General solutions to what are called differential equations. We've done a lot of the setup, we just haven't formalized this or practiced this. So general solutions to differential equations. And then another thing we're going to do is we're going to do volume of solids. So using integral calculus, we aren't limited just to area, but we can do volumes of solids. And there's kind of three main ways that we'll cover. We're going to do the disk method, the washer method, and by cross sections. Now something that we're going to write here, it'll make more sense when we do. We can do the volume of solids with regards to x or with regards to y. All right, there's our chart as it stands now for integrals. Thank you for watching.